In the following videos, we're going to look at a concept called Karnaugh maps, or also abbreviated as K-maps, and this will be a two-part video where the first part will be the sum of products and the second part will be the product of sums. Now up to this point, we know if we have a function given as f, or in this case, it's the variables w, x, and y, and it's expressed in the sum of products, we can take that to a truth table and write out all of our combinations, and we can determine when we get the values for 1. From that, we can express the function f in terms of w, x, and y, like we did right here. And from this, we would use Boolean algebra to make any simplifications that are able to be made. Now we're going to use the property of a plus a is equal to a, and simply duplicate this w bar xy term and add it on to the end of this equation. And now we're going to carry through with our Boolean algebra simplification. So we can group these first two terms to have w bar y times the quantity of x bar plus x. We know that this is going to be equal to 1. And then our second term is going to be w plus w bar in parentheses times xy, where again, this term is equal to 1. So our function is given by w bar y plus xy. And all of these steps are nice to know when you're learning the fundamentals of logic and electrical engineering, but what we want to do is take it a step further and start to make things easy. So to do that, we introduce a concept called K-maps. And with K-maps, we set up a table of however many cells that we have for combinations of our inputs. So in this case, we have 8 possible input combinations, so we have 8 cells. Now we're going to break up the map into w and then x and y. So w is going to be vertically, xy is going to be horizontally. And we're just going to list out all the possible combinations. Now this is where the trick with K-mapping gets a little bit confusing and you kind of have to memorize it. In terms of our input w, we have a 0 and a 1. And horizontally, we have 4 possible combinations, but notice the order here. So we have 0, 0, 0, 1, 1, 1, and 1, 0. So it's not really in order. Now the decimal equivalent for all of these combinations are given in the top right corner. So you can see w equals 0, x equals 0, y equals 0 corresponds to this combination here. And 0, 0, 0 would be a decimal 0. Now for K-maps, what we're going to do is take our sum of products and fill in the values with a 1. So now that we've filled in the K-map, we need to learn what we can actually do with it to be useful. And this is where we bring in the very important rule where we can group cells together. So you could have 1 cell grouped together, 2 cells grouped together, 4 cells grouped together, 8 cells grouped together, etc. Okay, so now that we know we can group them together, how do we actually group them together? Well, if we look at w as an input, we can see that the case where w is equal to 0, we get 2 values where we have 1s. And in those 2 values where we have 1s, you can see that y is equal to 1 in both of those cases. So the only differing variable is x. So we can group these 2 cells together. Now, if we look at these 2 cells vertically, you can see that x and y are the same, but w is varying between them. So we can group those together. Now, if we look at this horizontal grouping, this is where things get easy because we can see that w is 0 or w bar and y is equal to 1. So we have a y. And if we look at the vertical grouping, you can see that x and y do not change, but w does. So we don't care what value w is. We're always going to get a 1 if x and y are equal to 1 or high. And if we look back at the truth table, you can see that when x and y are equal to 1, no matter what w is, we get a 1. So now from these 2 terms, what we can do is say that f is equal to w bar y plus xy, which is exactly what we have from the Boolean simplification. So now we can start to ask the question, what is this K-map? How does it work? So now we want to prompt ourselves with the idea that what if we had a value here that was a 1 and a value here that was a 1. So we have that w is a 1, which would signify a w in this case and this case. We also have that y is a 0, so we would have y bar. And the only variable changing is x. but these two aren't next to each other, so how do we group them together? That's where we need to ask what this map really is. And while it's projected on a 2D plane right now, it's really a 3D object. So what we're going to do is essentially wrap this around itself such that we have a tube right here. We're going to take that tube and connect both ends so that we get a donut. And doing that, we have our numerical values in the same places. And what you can see is that the 0 and the 4, which were up here, are connected to the 2 and the 6. So what that means is we can actually have a grouping that wraps around, and these two can be grouped together. So let's look at an example where we define a function given by the sum of products, where we have a lot of products in that sum, and doing the algebra to try to simplify that would be very tedious. So what we're going to do, take all of these values and fill in where they are. So that being said, we can first group this top row together. We can group this inner block together. We can group these top two together. Group these bottom two together. And then from our donut representation, which doesn't change too much from the 3 variable case, we can group these together. So if we look at this top one, what we get is W bar Y Z bar. This bottom one, we get WX bar Y. This one that loops around, we get WX bar Z bar. This 4 on the second row ends up being W bar X. And this bottom quadrant becomes XZ. So now we can group all of these terms together, and that's our function. So in the next video, we're going to talk about the product of sums as compared to the sum of products, where in the sum of products we cared about the ones, and in the product of sums we're going to care about the zeros.